The NASA scientist who repaired a spacecraft from 15 billion miles away in the vast expanse of space, humankind's most distant emissary, Voyager 1, has been silently traveling beyond the reaches of our solar system for over 4 decades. Launched in 1977, Voyager 1 has since become a symbol of humanity's quest to understand the cosmos. It ventured into the unknown, bearing with it the hopes and dreams of a civilization eager to unravel the mysteries of the universe. Yet after more than 45 years of exploration, NASA recently made the difficult decision to officially terminate the mission, marking the end of one of the most extraordinary scientific endeavors in human history. The reason behind this decision was as remarkable as it was alarming. Voyager 1 had discovered something so profoundly significant that its continued existence posed a potential risk. Before we start, please don't forget to like and subscribe to our channel for more updates. Voyager 1's primary mission was to study the outer planets, Jupiter, Saturn, Uranus, and Neptune, but it quickly transcended this purpose. In 2012, Voyager 1 became the first human-made object to enter interstellar space, crossing the boundary known as the heliopause, where the sun's influence wanes and the interstellar medium begins. For years, the spacecraft continued to send back invaluable data about the conditions beyond our solar system, providing scientists with insights into the nature of interstellar space, cosmic rays, and the magnetic fields that permeate the region. However, it was during one of these routine transmissions that Voyager 1 detected something unusual, something that had never been encountered before. The spacecraft, now located more than 14 billion miles away from Earth, began transmitting data that baffled scientists at NASA. Initially, the signals were faint, almost indistinguishable from the usual cosmic noise that fills the void between stars. But as the team analyzed the data, it became clear that Voyager 1 had encountered a phenomenon that defied all previous understanding of space. At first, NASA kept the discovery under wraps, allowing time for its team of scientists to thoroughly investigate the anomalous readings. They initially speculated that the signals could be the result of interference from galactic radiation, or possibly an error in the spacecraft's aging instruments. However, as the data continued to pour in, it became evident that this was not a technical malfunction or a mere anomaly. It was something far more significant. Voyager 1 had stumbled upon what appeared to be a region of space where the known laws of physics were seemingly bending or breaking down altogether. This discovery set off a flurry of activity within NASA. Teams of physicists, astronomers, and engineers were brought together to study the data, and the findings were nothing short of astonishing. Voyager 1 had entered an area where the fabric of space-time itself appeared to be fluctuating. This wasn't just a minor disturbance. This was a full-blown disruption in the very structure of the universe. In this region, the usual rules governing the behavior of matter, energy, and gravity no longer seemed to apply in the way they did within the rest of known space. Particles moved in unpredictable ways, electromagnetic fields fluctuated erratically, and time itself seemed to warp and stretch in inexplicable patterns. As more data was transmitted back to Earth, the true scale of the discovery became apparent. This wasn't just a localized phenomenon. It was a vast region of space, possibly stretching for light years in every direction. It was as if Voyager 1 had stumbled into a kind of cosmic fault line, a place where the very underpinnings of reality were coming undone. The implications of this discovery were profound and deeply unsettling. If such regions existed elsewhere in the universe, it could mean that our understanding of the cosmos was incomplete or even fundamentally flawed. NASA scientists quickly realized that the potential risks associated with Voyager 1's continued exploration of this region were far greater than they had initially anticipated. As the spacecraft delved deeper into the anomaly, the signals it transmitted grew increasingly distorted. There were concerns that Voyager 1 could unintentionally destabilize the region further, or that its presence within this fluctuating spacetime could trigger a cascade of events with catastrophic consequences. Some scientists even speculated that the anomaly could be a gateway of sorts, leading to unknown dimensions or parallel universes, though this idea remained highly theoretical. The possibility that Voyager 1 could inadvertently cause a disruption on a cosmic scale forced NASA to make a difficult decision. After extensive deliberation, they decided that the safest course of action was to terminate the mission. Destroying Voyager 1 wasn't just about shutting down its systems and ceasing communication. It required ensuring that the spacecraft would no longer interact with the anomaly or continue its journey deeper into uncharted territory. The destruction process involved sending a final command to the spacecraft, instructing it to self-destruct in a controlled manner. The decision to destroy Voyager 1 was not made lightly. For decades, the spacecraft had been a symbol of humanity's boundless curiosity and ingenuity, carrying with it the golden record, a message in a bottle intended for any potential extraterrestrial civilizations. To terminate such a mission, especially one that had achieved so much, was a painful but necessary choice. The implications of leaving Voyager 1 to drift through a region where the fundamental laws of physics were in flux were simply too great a risk to ignore. As the final command was transmitted to Voyager 1, there was a palpable sense of loss among those who had dedicated their lives to the mission. But there was also a sense of awe and wonder at what had been discovered. Voyager 1 had done what it was meant to do. It had pushed the boundaries of human knowledge and revealed mysteries that were beyond our wildest imaginations. In its final act, the spacecraft had shown us that the universe is far stranger and more complex than we could have ever anticipated. The destruction of Voyager 1 also raised profound questions about the nature of the universe and our place within it. What was this anomaly? How did it come to exist? And what did it mean for our understanding of space and time? These questions remain unanswered, and it is likely that scientists will spend years, if not decades, studying the data that Voyager 1 transmitted in its final months. The discovery has already sparked a new wave of interest in the field of theoretical physics, with some suggesting that this could be evidence of phenomena predicted by string theory or quantum gravity, while others propose entirely new frameworks for understanding the universe. One of the most significant implications of this discovery is that it challenges the very foundation of modern cosmology. For centuries, scientists have operated under the assumption that the laws of physics are constant throughout the universe, that they apply equally to all regions of space and time. Voyager 1's discoveries suggest that this may not be the case. If there are regions of the universe where the laws of physics break down or behave differently, it could force a radical reevaluation of many long-held theories about the nature of reality. Concepts such as dark matter, dark energy, and the very structure of space-time may need to be revisited in light of this new information. Moreover, the discovery has implications for our understanding of the future of the universe. If these anomalous regions exist and are more widespread than we currently know, they could play a significant role in the ultimate fate of the cosmos. Could these fluctuations in space-time grow and spread, potentially leading to the collapse or reformation of the universe? Could they be remnants of previous cosmic events, such as the Big Bang, or evidence of future transformations that the universe will undergo? These are questions that scientists are only beginning to grapple with, and the answers could fundamentally alter our understanding of the past, present, and future of the cosmos. Another important consideration is the possibility of other intelligent civilizations encountering these anomalies. If such regions exist in other parts of the universe, it raises the question of whether other advanced species have discovered them and, if so, how they have responded. Could these anomalies be natural phenomena, or could they be the result of some advanced technology or intelligence that we have yet to comprehend? The discovery adds a new layer of complexity to the ongoing search for extraterrestrial life and civilizations, as it suggests that the universe may be far more unpredictable and dangerous than previously thought. The termination of Voyager 1 also prompts us to reflect on the role of humanity in exploring the cosmos. For all our technological advancements, we are still at the mercy of forces and phenomena that are far beyond our control. Voyager 1's mission was a triumph of human ingenuity, but it also serves as a humbling reminder of how little we truly understand about the universe. As we continue to explore space, we will undoubtedly encounter more mysteries and challenges that will test the limits of our knowledge and capabilities. Despite the destruction of Voyager 1, its legacy will continue to inspire future generations of scientists, engineers, and explorers. The data it transmitted will be studied for years to come, and the discoveries it made will undoubtedly shape the direction of future space missions. In many ways, Voyager 1's final discovery is a fitting conclusion to a mission that was always about pushing the boundaries of what we know and venturing into the unknown. While the spacecraft may be gone, its contributions to science and our understanding of the universe will endure. The destruction of Voyager 1 is a poignant reminder of the delicate balance that must be maintained when exploring the cosmos. For decades, the spacecraft served as humanity's most distant outpost, venturing beyond the solar system into regions where no other human-made object had gone before. Its journey took it across uncharted territory, delivering invaluable data back to Earth that reshaped our understanding of the universe. However, the final chapter in Voyager 1's story demonstrates that there are phenomena in space so complex and so dangerous that even our most advanced technology cannot fully comprehend them. Voyager 1's discovery of the space-time anomaly challenges not only our understanding of physics, but also our approach to deep space exploration. Since the dawn of the space age, human beings have been driven by a sense of wonder and adventure, seeking to unravel the mysteries of the cosmos. But as we delve deeper into the universe, we must also confront the possibility that there are regions of space where our current knowledge and tools may not be sufficient to navigate safely. The destruction of Voyager 1 also has profound implications for the future of human space exploration. Although we have long dreamed of sending astronauts to other star systems, Voyager 1's encounter with the anomaly serves as a stark reminder that space is not always a benign frontier. If such anomalies are widespread, they could pose a serious threat to future crewed missions, making interstellar travel far more dangerous than previously thought. The possibility that there are regions of space where time, gravity, and energy behave unpredictably complicates the already formidable challenge of traveling to other stars. In the context of human space travel, the anomaly raises questions about how we can ensure the safety of astronauts in regions of space where the laws of physics are in flux. Traditional spacecraft design is based on our understanding of Newtonian and relativistic physics, but if these principles no longer apply in certain parts of the universe, we may need to rethink how we build and operate spacecraft. Future missions may need to be equipped with entirely new types of propulsion systems, navigation tools, and shielding technologies capable of withstanding the unknown forces at play in these regions. Moreover, the existence of such anomalies could complicate the search for habitable planets. If regions of spacetime can become unstable, it may be possible that entire star systems could be rendered uninhabitable by such phenomena. This would significantly narrow the number of potential targets for human colonization, forcing us to be far more selective in our search for other worlds. We may also need to develop new methods for detecting these anomalies from a distance, ensuring that future missions do not inadvertently enter dangerous regions. At the same time, the discovery of the anomaly opens up exciting possibilities for the future of space science. If we can better understand the nature of these space-time disruptions, it could revolutionize our understanding of the universe. For example, some scientists have speculated that such anomalies could be linked to wormholes or other exotic phenomena that could allow for faster-than-light travel. While these ideas remain speculative, the discovery of a region where the fabric of space-time behaves unpredictably suggests that there may be pathways through the universe that we have yet to discover. If such pathways exist, they could dramatically alter our approach to space exploration, enabling us to travel vast distances in far less time than is currently possible. However, this would require a level of scientific understanding and technological development that is far beyond what we currently possess. It may take centuries or even millennia before we fully understand how to navigate and harness these anomalies, but the potential rewards could be immense. Voyager 1's final discovery could be the first step toward unlocking a completely new mode of space travel. Another important implication of the anomaly is its potential to affect the search for extraterrestrial intelligence. For decades, scientists have been searching for signs of intelligent life in the universe, using radio telescopes and other technologies to scan the skies for signals from other civilizations. The discovery of a space-time anomaly complicates this search as it raises the possibility that some regions of space may be fundamentally different from what we expect. If the laws of physics vary in different parts of the universe, it could mean that intelligent life in these regions might develop in ways that are completely alien to us, making it much harder to detect or communicate with them. In this context, the anomaly could represent a significant challenge to our efforts to find extraterrestrial life. It suggests that there may be regions of the universe where life evolves under completely different conditions, possibly even in forms that are unrecognizable to us. This raises important questions about the nature of life itself. What does it mean to be alive in a universe where the basic rules of physics can change? Could there be forms of life that exist beyond the traditional boundaries of biology, perhaps even life that is in some way tied to the fluctuations in space-time that Voyager 1 detected? The abrupt termination of Voyager 1's mission is not only a momentous event in the history of space exploration, but it also raises crucial questions about the future of humanity's quest to explore the cosmos. In ending the mission, NASA effectively acknowledged that the boundaries of human knowledge had been pushed to their current limits, and yet the deeper mysteries of the universe remain tantalizingly beyond our reach. The decision to destroy the spacecraft, while necessary for safety reasons, underscores the complexity and unpredictability of space, a domain where our scientific tools and theoretical models are sometimes inadequate to explain or manage what lies ahead. The region Voyager 1 discovered, where the fundamental laws of physics seem to falter, hints at the existence of phenomena that are far more intricate than anything we have previously encountered. While scientists have long theorized about the possibility of such anomalies, particularly in the context of black holes and other extreme environments, discovering one in a seemingly empty part of interstellar space was unexpected. This surprise underscores the immense gaps in our understanding of the universe, where certain regions may be governed by forces that defy the classical interpretations of gravity, electromagnetism, and quantum mechanics. This anomaly may be just the tip of the iceberg. Voyager 1's findings suggest the possibility of multiple similar regions scattered throughout the universe, potentially forming a network of anomalies that could change our entire conception of space and time. This realization has led some in the scientific community to propose that our universe may be far more dynamic than previously thought, composed of fluctuating regions where the constants of physics, like the speed of light or the force of gravity, are not as constant as they seem. If true, this would mark a paradigm shift in our understanding of the cosmos. What is especially intriguing is the idea that these anomalies could offer clues about the fundamental nature of the universe's creation. The sudden and radical disturbances in space-time could potentially be linked to the conditions that existed in the moments after the Big Bang. The universe's earliest moments remain shrouded in mystery. While current models suggest a rapid inflation of space-time following the Big Bang, the specifics of how and why this occurred are still open to debate. If Voyager 1's anomaly is somehow tied to these ancient forces, it could provide critical insights into how the universe came into being, offering a unique perspective that neither the study of galaxies nor cosmic background radiation has yet to provide. Even more astonishing is the potential that these space-time anomalies are remnants of other previous universes. Some cosmological theories suggest that our universe might be one in a series of cycles, where universes are born, expand, and eventually collapse or die out, only for another to follow. In this view, regions of unstable spacetime could be scars left by the collapse of an earlier universe, where the laws of physics from a previous reality bleed into our own. If this is the case, Voyager 1's discovery may provide evidence for the theory of a multiverse, an interconnected web of universes, each with its own set of physical laws and constants. The detection of such an anomaly also raises the possibility that our universe is not entirely self-contained. The idea of parallel universes, long confined to the realm of theoretical physics, suddenly seems more plausible. If space-time can become disrupted in such a manner, perhaps these regions act as bridges or windows between different realities, where alternate versions of our own universe, or completely alien universes, might exist. Such ideas have been entertained by theorists studying the quantum realm, where particles can seemingly exist in multiple states at once. Now, with Voyager 1's findings, we have tangible evidence that these kinds of phenomena might exist on a cosmic scale, rather than just at the subatomic level. Yet the implications of this discovery are as sobering as they are exciting. The region that Voyager 1 encountered could be hazardous, not just for spacecraft, but potentially for any form of life or matter that ventures too close. The unpredictable nature of the anomaly could mean that these regions act as traps, distorting space and time in ways that could make escape impossible. This raises an unsettling possibility. What if anomalies like these are scattered throughout the galaxy, hidden in the vast expanses of interstellar space? They could represent a previously unrecognized threat to future space missions, particularly as humanity begins to contemplate sending crewed missions beyond our solar system. The presence of such hazards introduces a new kind of challenge for space exploration. It is not just the technical difficulties of long-duration space travel that we must overcome, but the potential for encountering regions where the very fabric of reality behaves in unpredictable and potentially dangerous ways. This means that future explorers, both human and robotic, may need to be equipped with far more sophisticated detection systems that can identify anomalies in spacetime long before they are reached. Navigation would become far more complex, as mission planners would need to chart safe routes through space that avoid these dangerous zones. One of the most pressing concerns, however, is whether such anomalies are static or dynamic. If they are moving, then space exploration could become even more treacherous. Imagine a region of unstable spacetime drifting through interstellar space, potentially colliding with planetary systems or even passing through galaxies. The consequences of such an event could be catastrophic, with entire solar systems being disrupted or destroyed by the fluctuations in gravity, energy, and time. The thought of a moving anomaly brings to mind the natural disasters we experience on Earth, such as hurricanes or earthquakes, but on a cosmic scale. The possibility of dynamic anomalies raises questions about how we might predict or detect their movement. Would they behave like celestial objects, following predictable paths through space, or would their motion be governed by forces we do not yet understand, making them impossible to track? These are questions that scientists will need to address as they continue to analyze the data sent back by Voyager 1. Additionally, they will need to develop new models that account for the behavior of these anomalies, potentially drawing on both classical and quantum physics to fully understand their nature. Another fascinating possibility is that these anomalies are not natural phenomena at all, but the result of advanced alien technology. Throughout history, humanity has often attributed mysterious events to the work of deities or supernatural forces, only to later discover that these phenomena have natural explanations. But in the case of spacetime anomalies, we must also consider the possibility that they are the byproduct of some extraterrestrial civilization's attempts to manipulate the universe on a fundamental level. The idea of aliens with the ability to warp spacetime has been a staple of science fiction for decades, but the discovery of an actual anomaly raises the stakes considerably. If extraterrestrial civilizations exist, and if they possess technology capable of creating or controlling spacetime anomalies, then we are dealing with beings far more advanced than ourselves. Such civilizations could have mastered the manipulation of gravity, energy, and time to a degree that is unimaginable to us, using these skills to travel vast distances instantaneously, or even to create new regions of space. Voyager 1's discovery could be the first evidence that we are not alone in the universe, and that other civilizations have been altering its structure for purposes that we cannot yet comprehend. The implications of alien involvement in the creation of spacetime anomalies would be profound. It would suggest that the universe is not just a passive backdrop for the evolution of life, but a dynamic and manipulable environment that can be shaped by intelligence. This idea could lead to a complete re-evaluation of the Fermi paradox, the question of why we have not yet encountered evidence of extraterrestrial civilizations despite the vastness of the universe. Perhaps the reason we have not yet detected any clear signs of alien life is that we have been looking for the wrong kinds of signals. Instead of radio waves or megastructures, advanced civilizations might be altering the fabric of space itself in ways that are difficult for us to detect or understand. The discovery of a space-time anomaly could also have profound implications for our understanding of space travel. If these anomalies can be harnessed or controlled, they might offer a way to achieve faster-than-light travel, something that has long been thought to be impossible according to Einstein's theory of relativity. The idea that we might one day be able to warp space, folding it in on itself to create shortcuts between distant points, has been a dream of both scientists and science fiction writers for generations. But if these anomalies are indeed natural phenomena that occur throughout the universe, they could provide the key to unlocking this potential. Of course, the idea of using spacetime anomalies for travel comes with significant risks. The very nature of these regions is unpredictable, and any attempt to manipulate them could have disastrous consequences. Nevertheless, the discovery of a region where the laws of physics do not behave as expected suggests that faster-than-light travel may not be as far-fetched as it once seemed. If we can figure out how to safely navigate these regions, or even to create them artificially, It could revolutionize space exploration, allowing humanity to travel to other star systems in a matter of hours or days, rather than centuries or millennia. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us what you think Voyager 1 discovered before its destruction? We want to hear from you. Thank you for watching, and see you next time.